Yeah, we want to look at this particular problem here, where what you're doing is you're trying to find, okay, the shortest distance from a point, a fixed point, mainly uh, B at 4, 0, to a point on the line governed by the equation 3x plus 1. So as you can see, this has been drawn up in Sketchpad, and it says point A is free to move on the line, okay, as you see. Uh, so if we were to let and since it's free to move, of course, its coordinates, as we see here, are not fixed, okay, uh, much like they are fixed here at B. So as this moves along, it takes on different coordinates. And of course, as it takes on different coordinates, the distance from A to B is subject to change. And we're trying to find when is that distance going to be at a minimum. A couple things we're trying to find actually is what is the coordinates of that point A when that minimum is reached, and what is that minimum. So, okay, so instructions here say we can drag this along. We're watching how this value of the distance AB shrinks, and we're trying to capture when it is at its absolute minimum, which looks like we're rapidly approaching right about here. At this point, it starts getting about 4.11. It seems to be that. Now, previous problems told us that that minimum distance is obtained by determining the equation of a line AB, okay, um, which is perpendicular to the given line 3x plus 1. So if I were to ask for the equation of this line, its slope would be negative 1/3. And once we have the equation of that line, we could use the systems of equations to find the intersection. And then having gotten that intersection, we can then, of course, use the distance formula from A to B. This optimization approach is going to actually streamline this a little bit for us. So it looks like we found this, okay? Again, we're allowed in Sketchpad to look at all the infinite possibilities, but there is only one which satisfies that. So we're going to step out of Sketchpad here for a moment, okay, and follow the directions and see if we can determine analytically this same minimal value of as we've done here. So we'll be back in just a second. Okay, so we're back, and we're going to, as we said, we're going to follow through with this process. Let me get my pen back here. Okay, so we're going to find the distance from A to B. A was given arbitrary coordinates x, y, because they're free to move about. B has fixed coordinates in 4, 0. All right. The distance AB is, of course, using the distance formula, which is going to be x minus 4, the quantity squared, plus y minus 0, the quantity squared, which is just y squared. Okay. So this one expanded out is x squared minus 8x plus 16 plus y squared. Now, that is good as a formula, but we want the distance as a function, which means we can't keep two variables in this expression, okay? And we don't need to, because when we come up here, this says f of x is equal to 3x plus 1. Well, f of x, of course, is the same as y equaling 3x plus 1. And there's our substitution that we go right in there, okay? And when we do that, x squared minus 8x plus 16 plus y, which is now 3x plus 1, quantity squared. We now have distance as a function of x. Now we're going to clean that up, that x squared minus 8x plus 16 plus 9x squared plus 6x plus 1. And once we combine our like terms, 10x squared, okay, minus 2x plus 17 is, under the radical, is our distance as a function of x, okay? So what two things were we asked to find? Well, we're asked to find the point A, which has a minimal distance, okay? And we're asked to find that minimal distance. Well, as you can see here, this expression underneath the radical is quadratic. So therefore, this overall expression is quasi-quadratic, which means the x producing the minimum, and this would be a minimum because this quadratic component would open upward having a minimum, is always negative b over 2a when it's quadratic or quasi-quadratic. So negative b over 2a is the x-coordinate, which would be, of course, 2 over 20, which is, of course, 1/10. So x is 1/10, okay? The minimal distance will be d of 1/10, which just simply means plug that value 1/10 back up in this function, and you'll have the minimal distance. And the y-coordinate, of course, is given by the equation 3x plus 1. So that makes that 3 times a tenth, or 3/10 of 1, so it's 1.3. So the minimum, the point at which the minimal distance is obtained is 1/10, or 0.1, and 1.3. The minimal distance, I leave that to you to compute. You just take that 1/10, which of course was from the negative b over 2a, and plug it back into there, okay? And when we go back, I'm going to try to drive this thing right to that minimum distance, okay? And my resolution here isn't quite good enough, okay? But there is, okay, all right, there's my minimal distance, because there's my point, 0.1, 1.3, which we found, okay? And then my minimal distance is 4.11, which is what you should find, okay, when you evaluate this function, the distance function at 1/10. So I'll leave that for you to do, and that hopefully explains that problem a little bit better for you.